Close this. Okay. Assalamualaikum and very good morning. So sorry for the bit delay there. Okay, so welcome back. And in today's chapter, we're going to talk about real-time operating system. Okay, so this is chapter 11, mostly theoretical. So let's have a look. Okay, so in this chapter, we're going to start by looking at what's an operating system generally, and then followed by what is an embedded operating system. Okay, and finally, what does it mean by real-time operating system? So we're going to go and we're going to narrow down starting from operating system. Okay, so let's begin operating system. So basically, simple embedded systems are normally microcontroller based, where you can actually implement your program using a sequential program or a single task application. And which means that, for example, if you're trying to do, let's say, a traffic light controller, okay, a controller that's going to control the traffic light, or perhaps a controller for your air conditioning. So in your room, you got this air conditioner, right? And then you want to measure the temperature, and then you want to decide whether to turn on or off the compressor, okay, and so on. And some aircon can also, set timers, okay, and you have different modes on the aircon as well, cooling and just fan or drying and things like that. So for things which are simple like this, perhaps you can implement using a single microcontroller, and your program can be sequential, and then only running one program, so single task. And if you want to do some sort of multitasking, perhaps, okay, then you can do what we call interrupt driven. Okay, so you can have interrupts to switch between different parts of your program. Okay, but you still have just one program running, but you can trigger different parts of your program using an interrupt. Okay, so that's one way of doing it. Okay, so in this case, if you want to use operating system, it is really like overkill. Okay, why? Because an operating system itself is a software. Okay, and it will require memory usage and then processing power and so on. Okay, so if you see when you buy a new phone, it says it's a 64 gig storage, but when you turn on the phone and it says only maybe 50 gig storage available. And the reason is because some of the storage has been used by the operating system. And when you have like a 4 gig phone, okay, 4 gigabyte RAM, or on Windows or laptop, you have an 8 gig laptop. When you come to your desktop, you only see maybe 6 gigs available for you to use because some of the components of the OS is taking the memory's usage. Okay, so that's an overhead. Of course, you have the benefits of OS. Okay, we're going to see that later. But the first point here is that running an OS will incur some sort of overhead. And when you have small problems and small applications, perhaps you don't need an OS. You can simply write your program directly. Okay, so just a sequential program running, no OS. Okay, so what's an OS? Well, it's a software or a program that provides an abstraction of the physical machine through simple interface, and each part of the interface is a service. Okay, so what it means is that you have this laptop, right, and you are running Windows or Linux, right? So you can write programs that read and write data from the drive. Okay, you can use fopen if you're using C, and fopen allows you to open a file from the drive and so on. Okay, and that's all that you need to know from your application. From your application perspective, you just use fopen and then provide the path of the file, and then other options such as read and write and so on. But it's really abstracted. That is the path. Let's say C blah 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 blah, or maybe E blah blah blah. Let's say drive is E. E could be a SATA connected drive internally. E could be a PCI Express drive connected internally. E could be an external USB drive. E could be a flash drive. E could be a drive over the network, and so on. Okay, or E could be a FAT32 formatted drive. E could be an extended for Linux drive. E could be an NTFS formatted drive. So for fopen, you don't really have to worry about that. Is simply opening a file over a certain location, a path, whether the formatted drive format, where the drive is connected over USB protocol or connected over PCI Express, or it's a network drive, or it's a Google Drive, it's a Dropbox. You really no need to know because it's abstracted. It's the same thing like you have seen the hardware abstraction layer in the STM32. You simply say write something to the pin. Really doesn't matter on the hardware. How is it connected? It is all handled by the driver. Okay. So another thing is that OS is also a resource manager. So resource means on your computer you have a couple of different resources. Resource in general means something that you have in limited amount. Okay. So you have limited amount of memory, that is RAM. You have limited amount of, let's say, bandwidth over the network, right? You have a 100 megabit connection, so there's a limitation there. You also have processing power limitation. That is, you have, let's say, dual core system, quad core system, and tops at 4 gigahertz. That's the fastest it can go, right? So we have limitation in all of these components in terms of resources. So if you have a program running, let's say Photoshop, you don't want Photoshop to take all the 8 gigabytes of memory on your system. Otherwise, things like antivirus, things like disk cleanup, things like other things that's running in the background cannot run. At the same time, if you're rendering something in Photoshop, applying some filters, and it's taking so long, okay, you shouldn't allow that Photoshop takes all the CPU costs to the max. Okay, why then? If you have any other important task coming in, it will not get the time to run on the CPU. So we don't want that. So we want someone to manage so that Photoshop gets to run, and if there's another task, it also gets to run, and then we can switch between them. Okay, so OS is a resource manager. Okay, so it needs to manage all the resources, including the bandwidth also. Okay, so a simple thing like internet bandwidth, that's also important. If you're watching YouTube and at the same time you're downloading something over the internet, well, you can delay a bit the download as long as the video playback is smooth. You don't want the video playback to get stuck and the download goes very fast. You want it to work seamlessly. So that would be much better, right? So you have to maintain quality of service, QoS. Okay, so that's something that the OS has to do. Okay. So down there is written there, OS provides access to physical resources like hardware and USB port and hard disk through the drivers. So just like what you have seen, you access the devices through some API, and the API talks to the drivers, and the drivers actually perform something on the hardware. Okay. Why do we need an OS? So since it's an abstraction, it cuts down your development time. It gives you less spotting efforts. It gives you better reusability. What it means is that if I want to write a program that's going to read and write an SD card and store images from a camera and so on, well, if I don't use an OS, then I will have to study all the specs for how to write SD card, how to format the SD card, and then what is the file format, how's the picture looks like, what's the JPEG file format, and so on. You have to do a lot of work there. But if you have an OS, then you just use the OS APIs, and the rest will be handled by the OS. Okay. So why do you need Windows 10? Why is Windows 8 not enough? If Windows 7 not enough, is Windows XP not enough? Well, you have to see. Then during Windows XP, you don't have PCI Express. Okay, during Windows XP, you don't have. I think we don't have what we have. We don't have USB 3. You don't have USB-C. Perhaps you don't have 4G at that time, so you don't have 4G modems also. What are the reason? You don't have a 4K monitor at that time. You don't have, very rarely, some computers use multiple monitors. You don't have HDMI at that time. You don't have DisplayPort at that time, and so on, right? So if you just use Windows XP today, then a lot of these things can't be done. So if you really want to use Windows XP and you want to use an HDMI monitor, then you really have to program the device yourself and so on. So the OS provides you this facility easily. So by upgrading to the recent OS, it now supports newer technologies. So all you have to do is just update your program based on the API, and the rest of the thing is done by the OS. Okay, so that's the thing. So OS allows you to develop faster because a lot of the low-level things and a lot of the common things are handled by the OS. Okay, in other words, everybody needs to write something to the file. Everybody needs to access a hard drive. Everybody needs to send something over the internet. Everybody needs to connect to 4G modem or access a webcam and stuff like that. So that's like a common thing. So the OS provides you with that. Okay, other than that, as like I mentioned, it is a resource manager. Okay, so it keeps resources busy. So that's also one important thing. An idle resource is actually a wastage, okay, unless you are saving energy. So if you're not running in energy saving mode, then if a resource is not being utilized, then it is a wastage. So if you have a 1 terabyte drive in your laptop and you only use 500 gigabytes of it, and you always try to keep 500 gigabyte empty, then actually you're wasting the 500 gigabyte, okay, because it's there, but it's not being used. If you have a 16 gigabyte memory system and you're just using 4 gigs of memory, then the rest of the 12 gig is a wastage. Okay, it's still powered on, but it's not being used. So you will see some modern operating system. They will try, like Windows, when you have 8 gigs of memory, you will see it's using 6 gig. When you plug in 16 gig of memory, it's using 12 gig. When you put 32 gig of memory, it's using 24 gig. I say, the more memory you put, the more you use. I know it's actually caching things in the memory because it's utilizing the memory to the best. Okay. What else? Avoid conflicts. Conflicts means as simple as two programs printing to the same printer. One PDF, you're printing 20 pages of PDF, and the other one is printing 20 pages of Word document. And it's not done yet printing the PDF. You don't see the papers come out in the wrong order. One page of PDF, one page of Word. You don't get see that things got mixed up because someone needs to maintain the conflict. Okay, put in the right queues, provide locks so things don't go wrong. Okay. For certain application where you need immediate real-time response, which we're going to talk, then you have to have an OS that minimizes response time. So it needs to be reactive, it needs to be real-time. Okay, so it needs to respond immediately. So depending on what you want to do, choosing an OS is important because why? Because high have efforts when porting to a different OS. Okay, so again, also because of OS also has an impact on the amount of resources needed. So, for example, you are currently targeting a system, let's say Windows, using Windows and targeting Intel processor. And then maybe 2 years down the road, you want to choose a different processor. You want to move to, let's say, an ARM processor. Okay, whatever applications or customized applications running on Windows, very hard to port to an ARM if there's no Windows for ARM. Okay. If you have chosen a Linux, then it's easier. Linux running on Intel, there's a Linux port for ARM, so not much changes. You just have to update the OS for the new processor and maybe perhaps update your application a bit. Then easy for you to port from one system to another system, another platform, okay? Because you choose a good OS, okay? Other than that, resources. So this always, when you have limited resources, you have to choose. For example, you have a smartwatch, what kind of OS you want to run on it, okay? You can't run a very big OS there. If you have a smart printer, like the ones that have 3-in-1, and then you can put in an SD card, you can print direct from the SD card. It's network connected, it got Wi-Fi. You know those kind of printers, right? They are running an OS as well. So you can put a big OS there, but then you have to put more RAM and more flash memory and so on, and that makes the printer expensive, and we don't want that. Other than that, maybe TV. You can buy TV today, and some TVs are with Android, some TVs are with Tizen, some TVs are with, I don't know, some other operating system. So depends. If the manufacturer, let's say Samsung, wants to keep the cost down, then you want to choose an OS that is small, so you can put less memory, and that saves costs. Okay, but of course, using a customized OS means if your YouTube application on your smart TV is outdated, then someone needs to update for that particular chip. Okay, otherwise, if you use a generic Android-based what we call OS, then it's easy. You can always update from the store. So those are some of the things you have to consider. Okay, so you can run ARM with an OS. So depending on the series, some series you have 64-bit. For example, the ones you have in your phone is a 64-bit. So it runs Android, and the same 64 bits in an Apple phone. It runs iOS. You also have the new Mac with a 64-bit ARM. Then it runs Mac OS, and some servers from AMD are running on ARM processors, so they run some sort of Linux system there as well. There are also ARM-based laptops from Microsoft and Surface X, and that also runs an OS. Okay, so yeah, you can run OS with an ARM processor. Okay, and depending on your application, whether it's a complex application, whether you need it or not, when you need a full-fledged OS like Windows or Linux, or when you need a limited OS just to do several things. So depending on your problem. Okay. So again, some things you don't need to have OS. So some applications where you best run with the OS is example is When you need to do multiple sophisticated tasks, for example, a GUI with network communication. So if you have something complex like that, then perhaps it's good to run an OS. Okay, maybe your in-car entertainment. Okay, you have that LCD display where you're going to show the mapping, so the user can choose maps, or you can just user can choose play media. The user can tune to radio. When you put in reverse gear, it changes to reverse camera. It can show the fuel consumption. What else can it do? Normal things inside a car. Or something can say, okay, connect to phone, and you can display what's on the phone, mirror the thing. You can also connect to your Bluetooth phone. So a lot of things there, right? Kind of complex thing as well, right? So yeah, you will need an OS for that. Okay. Application that need to use standard protocols. Okay. TCP/IP network, USB. So if you want to build a device that you need to put USB protocol, you want to put networking on it. Trust me, you don't want to write everything from scratch. So you probably need a help from a driver library if you really want to run simple applications. But if you have complex application, then maybe you just want to go for a full OS. Okay. So if you have a full OS, for example, you can run Linux on it, strip out all the GUI, and then your media player, you can just open a VLC, strip the what we call the close open buttons. So you don't have to worry too much. You just have to customize it rather than build everything from scratch. Okay. So when you need real time, we'll talk about real time in a while. Then you can consider real time operating systems. So these operating systems are designed to meet time deadlines. Okay, so timing. Okay, so it's for meeting times. Okay, time deadline. Okay, so a couple of concepts. First of all, multitasking. So when you have an OS, then it makes it feasible to run multiple applications at the same time. On your phone, you open your chat, and while you're chatting, you can switch to your, let's say, Facebook, and then share a file back to the chat, and links, so on and so on. So that's multitasking. So multitasking is running multiple independent applications, and this is possible because the OS is switching the context. Okay, and if you have a fast processor, then it's easy for you to execute or switch between contexts. If you have multiple processors or multiple cores, then the OS can decide to schedule each task to a dedicated processor. Okay, so if you have if you have like 128 processors and you're running 50 programs, so the OS can actually distribute the work across the processor cores or processors. Okay, but that's a complex thing to do. Okay, scheduling is a complex thing. It's a complete big topic. When you should schedule, when the processor is in low power mode, should I schedule to it? When I schedule something to a processor and it has done its work, should I schedule a new thing on the same processor? So there's a lot of things to be considered there. But the point here is that OS can do that. Okay. And then what else we need when you have a multitasking program, you must communicate between the processors, or the processors mean program. That's why in Windows Task Manager, if you go under details, there's process. They call it process. Process means program. Okay. So how do I communicate between one program and the other program? When then we have things like inter-process communication, pipes, and sockets. So socket is the one that you have. You open a socket and send data over the network, right? Or the simplest one is copy paste, right? You copy something, it goes to the clipboard. Then you paste in another document, it comes from the clipboard. So that thing is actually inter-process communication as well. Okay, so you're transferring through a global memory called clipboard and transferring the data between them. But of course, there are other things like IPC, where you can communicate directly between one program and another program. Extending the concept to within a program is called multi-threading. So multi-threading means that multiple things are running in the same program. So if you have multiple programs running, we call it multitasking. If you have multiple things running in a program, we call it multi-threading. Okay, so the simplest example I can think of is, let's say, Microsoft Word. As you type in Microsoft Word, you see the screen gets updated, right? Every time you type, your screen gets updated. So that's what we call graphics being updated. So that's one task happening. Okay, just 1 second. Just 1 second. Just 1 second. Uh, okay, coming back to this one. So Microsoft Word, when you type something on the screen, it gets updated, right? The screen gets updated. So that's one task running. That is refreshing the screen. So actually, it's a complex thing, lah. You have to render to the screen and then push it to the graphics card. That's done by the OS, but at least you have to update the screen buffer in your application. Okay, and then as you type, you'll see that red line coming up. That is when you have a spelling mistake. So a spell check is also running. And then you have a green one, that's a grammar check is also running. And if you realize in Microsoft Word, you can file print and the print goes to the background. And then while you can still do something onto the document. So there are a couple of things can happen at the same time. Okay, so in the same Microsoft Word, so we call that multi-threading. Okay, so the difference here is that when you have a thread, okay, thread means a particular unit of a task. PM Munim is going to talk about that in the afternoon class, but thread is a unit of task inside the program. So the thing is that multi-threading means the threads are accessing the same memory space. So they share the memory space. We call it multi-threading. But tasks, they don't share the memory space. Microsoft Excel and Microsoft Word, they are different tasks. They don't share the same memory space. So they can't write over to the other memory space. Okay, otherwise it will be a fault, memory fault. Okay. To do that, you have to use IPC or any other thing. Okay. In the core of the OS is what we call a kernel. Okay, so the kernel is the core. This is where all the important things happen. Okay. What is PM Munim asking? Which channel? Just one second. Maybe it's asking for the link. Give me 1 second. Send him the link. I think. Give me 1 second. Just send him the meeting link. He's joining a bit late. Okay, so the core of the operating system is called the kernel. Okay, so on Windows is kernel 32, the name of the file. Okay, what happens in the kernel? Only the important things such as memory management, scheduling, and multitasking things. That's all. Anything else than that, such as GUI, you see the buttons on your screen, drivers, and all of those things are outside the kernel. Okay. Of course, in the past, okay, on Windows we have kernel mode and user mode. Some things do run in kernel memory space, but now most of things have been shifted out. That is to provide stability to the system. So anyway, the core of the system is kernel. Instead, that is an important thing called scheduler. A scheduler means that if I have 2 or 3 things to do, what is the best way of doing them? So if I want to wash my clothes and eat a burger and also watch TV, what is the right way of running these 3 different tasks? Okay, so what I can do here is that go to the laundry in my house, okay, laundry room, and wash my clothes. That will take an hour, and I just wait there. And then when I finish washing my clothes, I'll go to the next one, eating a burger. That will take me 20 minutes. I'm just going to eat my burger. After that, I'm going to go and what we call watch TV. So this is like serial execution. So it's very inefficient. So I must do something so that I can run these things at the same time, or at least switch between them and give a best performance. So the OS can schedule. Okay, so let's go and what we call start the laundry. So once the laundry has been started, it can switch to the eating burger, and then it can switch to watching TV, and then switch to eating burger. Because you are one processor, okay, of course our mind, we can look and eat at the same time, but assume you can't, so we're switching between the 2 things very quickly. So you take a bite, you watch the TV a bit, you take a bite, you watch TV a bit, let's say, and suddenly there's an important task coming in that is raining outside, and you have some clothes outside, let's say from previous day, and you need to bring that clothes inside. So that's an important task coming in. So the scheduler will have to say, okay, eating and watching TV must be paused at the moment. And then switch to that more important task. We go and take the clothes inside, and then once we complete that task, we can switch back to that lower priority things. So I need to schedule these things properly. It's the same thing with you. I give you an assignment today, and then you will schedule that maybe when it's closer to the deadline, because you may have other important work things to do. Okay, or perhaps another important personal thing to do. So okay, you're free tomorrow, for example, a holiday in Penang, let's say, but I have other important things to do rather than assignment. So I can schedule first. I need to go to the clinic, I need to fix my car, those are more important. And then once I finish that, then I can switch to my assignment, but then I have to report something to my manager, so do that first and then switch between them. So scheduling, so that's what the kernel does. Okay, so a couple of different algorithms to do scheduling. We have first in, first out. The first task that comes in, that is the first one that we are going to settle. Okay, the second one is round robin, which means we say, okay, in one day, I am awake for, let's say, 24 minus 8 hours. I don't get 8 hours sleep, so let's make it 4 hours, make it easy. Sleep for 4 hours, I have 20 hours left. So I have 5 things to do. So I'm going to give each task same amount of time. So the first task assignment, I'm going to spend 5 hours. After finish or not finish also doesn't matter, it's going to get 5 hours only. After that, I'm going to spend 5 hours for personal time, eating, washing, jogging, watching TV. After that, 5 hours for work from home, okay, Intel work, and then 5 hours for family. So I'm going to give each task same amount of time, and I'm going to cycle through them. Okay, so we call this round robin. The other one is priority. Priority means that every task is given a certain priority to execute. Okay. What it means is that even if I'm doing something with a lower priority, when something with higher priority comes in, it must be executed first. Okay. So this may not be first in, first out. First in means that, okay, the first thing today, I'm going to give you an assignment today, but the deadline is after 2 weeks. So, that's the first thing that came in, okay, the assignment. But maybe tomorrow, something else that comes in which is more important. Because that is more important, although it came in later, the first in, first out, you cannot do lah. You have to execute the one that has the earliest deadline. So that one has a deadline in 6 days, so you have to do that. The one that came first has a deadline of 14 days, so we can delay that. So those are the things that we have to consider. Okay, scheduling. So if you're good at scheduling, you can manage everything. Okay. Okay, so when you switch between one program and another program, it's called context switching. Okay, so if you're old enough like me, okay, I'm significantly older than you all. Okay, 2021 means I'm very old. Okay, I don't want to tell you how old. You can guess. The correct guess will win a lottery today. Okay. Okay. Uh, which one is 05? Which one is 06? First one. Oh, okay. Never mind. Okay. So if you realize, long time ago, maybe 1990s, I remember my friend bought a Pentium processor desktop. It's called a P90 Pentium, 90 megahertz at that time. That was a single processor and a single core. And later, when I entered the university, another friend of mine bought Pentium 4. Wow, Pentium 4, Pentium 4, the first one. Also single processor, a single core. But even during that time in 1990s and in 1998, when I went to the university, right? You can do multiple things on the computer. With Windows XP, you can play a video. At the same time, you can download something, and at the same time, you can browse a website, and you can type something in Notepad, and maybe and also chat. At that time, it was ICQ and MIRC. Okay, what else? The player at that time was the Real One player, and also to play MP3, we have Winamp. Okay, so those are the things we had that time. But you can do many things at the same time, right? But you only have one processor. So how do we do that? We switch between the tasks. So this is where the scheduler comes in. It will give a little bit of time for media playback, let's say 5 milliseconds, and then after time is out, the media player is being paused, and then it switches to the next task, and then 5 millisecond pause, and then it switch very quickly between the task, and you see like everything is running at the same time. But of course, as you open 10 programs, as you open 15 programs, you see the video playback starts to stuck, and then download becomes slower and things like that, because now you're switching over 20 programs, so things become longer. Okay, so then you see performance degradation. Okay, now the problem is this. Since I only have one processor, which means I only have one set of registers on the processor. For example, on the ARM is R0 to R15. So if Microsoft Word is using R0 to R15 with its own contents, the moment the OS decides to switch to a media player, let's say Winamp, if you do not know, you can Google that. Winamp is an MP3 player during the old days. So when it switches from Microsoft Word to the media player, MP3 player, because you want everything to look like it's running at the same time, then the MP3 player is going to use the same R0 and R15. So if I overwrite the R0 and R15, R0 to R15, whatever the data is, that one of it is program counter. Of course, you don't overwrite that, but the data, if you overwrite those data, when you switch back to Microsoft Word, it will be in corrupted state. Okay, because my data has been destroyed by MP3 in the last switch. So in order to preserve the state of a particular task or thread running on the system, then we need to do saving. That is what we call context switching. So the moment I want to switch from Microsoft Word to task to Winamp player, which is done by the OS, okay, in the background, the OS is going to take those registers which are being used, and it's going to push it to the stack. Okay, going to push it to the stack. Okay, and then it switches to the other program, and the program loads its own stack registers and continue executing. The moment it wants to switch back to Microsoft Word, it's going to push it back and then pops back the contents for Microsoft Word and continue. So every time you want to switch, you save it to the stack. Every time you return, you load it back from the stack. So this gives you this adds extra overhead. Okay, which means now in order for me to switch, I need to save the context. Okay, that's written in the second point there, because I'm not reading the slides, right? The thing is that written there is saving and restoring. Okay, restoring. Okay, so I need to do this switching. So why I need to do switching between applications? Because I'm doing multitasking and multi-threading. Why do I need to do multitasking and multi-threading? Because I want things to run seamlessly. Other than that, I want to make the CPU become efficient. Why? Because it could be I double click something from the drive, opening a file. So the OS is busy loading data from the drive into, let's say, Microsoft Word. You're opening a Word document. So currently IO is busy, but the CPU is pretty much free. So why don't take the opportunity that the CPU is free and let something else run that needs to use the compute power? Okay, use the CPU. Okay, so the OS needs to optimize the usage. If you're busy using the network and the drive, then the CPU is free. So let Photoshop use the CPU for the meantime. So then it becomes efficient. Okay, so that's the reason why you want to do switching. And of course, so everything looks like it's running at the same time. It gives you that good feeling. Okay, but switching will require you to save the contents of the registers to the stack. And then when you switch back, you need to restore. And this adds extra usage of memory, and this will also add extra overhead. So when you have a lot of applications running, then there's a lot of pushing and popping from the stack. And when you have limited memory, then there's a lot of pushing and popping to the stack that is in memory. And the memory is not enough, then the OS is going to do virtual memory that's going to pushing and popping to the drive as a virtual memory. Then you're going to have more overhead, and it becomes slower and slower and slower. Okay, of course, when you have multiple processors or multiple core on the system, then what you can do is you can schedule the task on independent cores. Then there's no need to do switching. Okay, so you can reduce the switching. So that will actually significantly improve the performance. So even if you have a 4 GHz system, which is single processor, single core, versus a 2 GHz system with quad core, when you have multiple tasks running, not single task, multiple tasks running, then quad core systems may be faster than the single core system because of reduction in switching and context switching and dedicated CPU registers for each of the tasks. So you may see better performance. I can't say for sure, depend on your application also. Okay. Two types of OS, how it performs multitasking. One is preempt, one is non-preempt. So non-preempt is called cooperative. Okay. What is preemptive? Preemptive means that the OS is going to run a task, or when you have multiple tasks running, it's going to give time quantum. So I give every task 10 milliseconds to run. Okay, 10 milliseconds to run. Or if I'm doing a discussion in class, I have 62 students right now, is it? Let me just check. How many people I have in my class today? 49. I have 49 excluding me. That makes 48 students. So if I want to ask opinion from you, okay, dear students, I want opinion from you. So I say, everybody, only 30 seconds. So you're only allowed to talk for 30 seconds before I switch to the next person. So I am an OS with preemptive behavior. Why? If you start talking for 30 seconds and the moment you reach 31 seconds, I say, okay, stop. It's enough time for you. The next person. I don't allow you to go beyond that 30 seconds. Okay, that is how an preemptive OS works. It will provide the time quantum for every program running on the system, and then it switches between them. If the program did not complete its task, in that 30 seconds is very large actually for an OS. Let's say 5 millisecond also very large, but let's say 5 millisecond. If you did not complete that task in 5 millisecond, you will be stopped and the OS is going to switch to the next program. Your context is going to be saved, and then we will go to the next program, the next program, the next program. In the next turn, when it comes back to you, you can resume back from where you left. Okay, so you will get 5 millisecond in that cycle. Okay, so that's good. Why is that good? Because if I have a program that has hanged, okay, crash, Photoshop crash, or what is a famous program that crashes, that just hangs forever, okay? So if the program hangs forever, it will get its 5 millisecond quantum, and it hangs in that 5 millisecond time. Then after that we can just stop it, not stop the program running. We just stop its operation. We switch to the next program. So the next program, let's say, is zipping a file. Then the zipping a file will continue running. After 5 milliseconds, you go to media playback. So you have some video being played for 5 milliseconds, then switch to the next program. And then when I come back to the first program again, you are hang, right? Continue hang for another 5 milliseconds. And then I go to the next program, and then switch back. You still hang, continue hang for 5 milliseconds. So what happens here is that only the program that hang will hang forever. The rest of the program will continue running smoothly because they get their time to run. Okay. The opposite is non-preemptive. The non-preemptive, the OS will allow you to run completely. So if I'm running a Photoshop and it hangs, then everything hangs because Photoshop never releases the CPU. It forever hangs on the CPU, so other programs become hang also. So you start to click start button, cannot click. You press Control Alt Delete, nothing appears. You want to Control Tab to switch between tasks, cannot. Everything hang. Okay, but you don't see that nowadays lah. Sorry. Okay, so that's preemptive and non-preemptive. Okay, so just a quick one. The OS will ensure context switcher is invoked regularly. Corrupted tasks will be switched out, but it's okay. You will keep on corrupted forever. Okay, tasks may be switched out at inappropriate instances. Okay, so if you're updating an array, you may get interrupted halfway, but it's okay. You can resume in the next cycle. So context switcher does not know what the program is doing. It doesn't have the details of the task currently running. Okay, so it will just be conservative and save the context. Okay, everything in the register you just save. Okay, the context switcher or external timer is needed because we want to switch every 10 or 5 milliseconds, 2 milliseconds, then you need an external timer that triggers that. Okay, so we need this kind of preemptive OS for real-time system. Okay, what about non-preemptive? So for non-preemptive, task events will always be completed before it is swapped out. So again, if the program does not complete, still running, you cannot run another program. Okay. So the context size is more compact because we exactly know what needs to be saved. If the program is not cooperative, that is, it hangs and so on, then the overall system performance is degraded. So other tasks can't run, other tasks will just have to wait for you to complete, and so on. Okay. So the point number 4, if a task is corrupted, then the system becomes inoperable. Maybe you can open Windows 95, Windows 98, sometimes in Windows XP also. If Internet Explorer crashes, everything crashes. Okay, everything crashes. Okay, but today it's not like that. If one task crashes, then the system just runs. Even if Windows Explorer, I'm not saying Internet Explorer, Windows Explorer, the one you have the start menu and the desktop, even if that crashes, it's okay, but just restart, right? You will see the screen go blank. Just a desktop background, and then the start menu will reappear and everything comes up again. Okay, just don't crash the kernel. If the kernel crashes, blue screen, that's it, cannot do anything. Okay. Okay, so that's the end of part 1, where I talk about where I talk about just operating system. Okay, since I started at 9:18 approximately, or 9:20 it was. So I'm going to continue now. Okay, and I think I started at 9:22. Okay, so I'm going to continue now 20 more minutes before I give you a break. Okay, so let's continue to the next part, which is embedded OS. Okay, so what's an embedded OS? Is just like a desktop OS, except that we have several other constraints. First of all, less services are provided, which means less services by the OS, which means the programs that come with the OS, okay, the facilities that the OS provides, so less, lower memory requirement, okay. For example, if you want an OS that runs on a robotic vacuum cleaner, okay, those are kind of intelligent things as well. Don't buy the cheap one, don't buy the few hundred ringgit one, buy the expensive one, the 1,000 ringgit one. Those are more intelligent. So they have an OS running in it, okay, but it's not going to be using 4 gigs of RAM and 1 gigabyte of hard disk space. It will be very compact, okay. And for these embedded systems, most likely it runs directly from ROM. Uh, if you have a smart, let's say smart fridge, uh, then everything is running from the ROM, but you can update it anyway. And then no keyboard and mouse required. Okay, because for these systems, it's not for user to use directly the OS. The OS is already starting to manage the thing, so you won't find a mouse and keyboard uh, on your what we call on your washing machine, or on your smart fridge, on your smart TV. Someone can argue smart TV can, we can connect Bluetooth mouse and keyboard. That's true, but that is to run the application. That is to put input to the YouTube or Netflix. Okay, that's for that. It's not for configuring the system. So when I say no keyboard or mouse required, means that not to configure the system and so on. Okay, that's purely managed by itself. Even if you have keyboard and mouse, it's probably just to input data from the user. So you can imagine a ATM machine is an embedded system. It's running an embedded OS. You may find a keyboard on an embedded system that is an ATM machine where you put in punch in your PIN number. Some of them are touchscreen. Some of them they have the physical keys. Okay. Yes, but that's not to configure the OS. It's just a method to input the data. But you will be surprised. Many of the ATM machines are running Windows XP or some old Windows version. Okay. Okay, special software. For example, you may have special drivers and special software which to drive very specific devices on that embedded system, such as flash disk, a touchscreen, tiny displays, gyroscope, accelerometer. Those are very specific things on embedded OS. Okay. What else? What makes a very good embedded OS? Modular. Means based on modules, so you can select the modules that you want. Scalable. Scalable means as you upgrade to a faster, bigger processor, it just works fine and better. Configurable. You want an embedded OS that, hey, if I want to install on this platform, it's not going to have any display, so remove components for display. Now I want to install it on an ATM machine. The ATM machine, I don't want to have any USB ports. Okay, disable or remove USB components. Okay, small footprint means a small size. You don't want it to use so much storage or memory. CPU support. Why? Because today you are stuck with a company, let's say called A. Tomorrow maybe the company goes out of business. You want to switch to processor B, or maybe company A now start selling the processor very expensive. You don't want to use that, or you want to let's say performance of company A is not so good. You want to switch to company B, better performance. So you want an OS that is also available for that company. Okay, so what it means is that, oh, Linux is available for x86, also available for x86 64-bit, also available for PowerPC, also available for MIPS, also available for ARM, also available for, I don't know, some other processor. Okay, so same Linux is available for many different processors. If you run, or if you build an in-car entertainment system running on Linux, if tomorrow you want to decide to change from, let's say, MIPS to ARM, then very minimal things you have to do because the OS is the same. It's available for the new chip as well. That's called CPU support. Okay. Difficult for Windows. Windows is only runs on x86. Also run on ARM with very limited capabilities. So if I really want to run my applications on ARM, then very difficult for me. Okay, many things doesn't work. Okay, device driver very important. Okay, That's also another problem, right? If you buy a laptop with Mac, then you have some very old printer in your office. It probably won't work. No drivers available for that. So you want to buy a device that the driver also available, right? So if you want to work with an embedded OS, you'll be sourcing LCD displays. You'll be sourcing what we call USB controllers for your product. You'll be sourcing what we call GPS for your product, and so on. And you want to make sure available device drivers for those products. So when you build your application on this embedded OS, hopefully the embedded OS can be configured with this product. For example, again, in-car entertainment, you have an LCD display, and then you have a processor in it, and then this display is also going to be connected to the engine control unit to show your fuel consumption and so on. Also connected to a GPS receiver, GPS receiver from company X, and then also connected to a webcam not webcam lah, camera at the back of your car, and that camera is from company Y. And so on, and it's a full HD, got 3 angles and blah blah blah, so many things, right? So you're sourcing from different companies, so hopefully it's very easy for you to interface with them using the device drivers. Okay, so what are the things you want to see in an embedded OS? Okay, real-time operation. That is, make sure the embedded OS, this is for application where you need real-time lah, okay, that the application can give me a correct answer. That's number one, at the right time. Okay, two things. The time factor is there. Okay, obviously there's no point giving me a wrong answer at the right time. Okay, there's no such thing as that. Obviously you want it to have, or you want it to produce the right output at the right time. Okay, so correctness is definitely there lah. Okay, but the timing is also there. So if I need the result today from you, and then you give me, if I need to decide something, hey, I'm in JB, I'm going to Singapore now. Okay, do you want anything? Okay, let's say Alan, Yap Yun Heng, I'm in Singapore right now. Do you want anything from Singapore? Can you tell me by 12 noon? Because at 1 p.m. I'm taking a bus coming back. That's sort of a real time. You reply my message at 1:30. Then the answer is no longer useful. Okay, even this correct answer, whatever I want, this and that, I think is useless. Okay, the deadline has passed. Whatever you tell me is no longer applicable. So real time is about that. Missing a deadline may result in catastrophic output. Example, let's say airbag system. The moment your car hits something, let's say the moment your car hit a car in front of you, at a certain speed, let's say 40 kilometers per hour, that is the minimum speed required. And the moment the sensor detects that there is a collision, okay, the sensor sends a signal to the controller. The controller must what we call deploy the airbag, and the airbag must open within, let's say, 100 milliseconds. Let's say that's a requirement. Okay, so if the airbag opens after, let's say, 500 milliseconds, that is 5 times later than required, then it's probably too late. Your head already hit the steering wheel. Okay, after that, it's no point. Okay, so that's a really hard requirement, really hard real time. You really need to submit it at you really need to produce the deployment of airbag exactly at 100 milliseconds. Otherwise, there will be a catastrophic output. That is, the person's head will already hit the steering and he will probably die already. Then after that, after they die already, then only open the airbag. What's the point? Okay, so that's what we call timing is very important. Okay, reactive operation needs to consider worst case. Okay, so you may have things coming later but have an earlier deadline. Okay, my assignment may be given earlier, but the deadline is so further away, it's okay. But maybe tomorrow for a different class, the assignment comes later, but has a sooner deadline. So you need to be reactive. You need to schedule that, this needs to be done first, even though it came later. So I need to switch tasks and handle this one first. Okay, and at the same time, make sure everybody is happy. All the tasks are actually handled with the right time. Okay, everybody reaches their deadline at the same time. Okay. Configurability, this one I mentioned just now. So if you have built an OS such as Windows CE long time ago, Windows CE Compact Edition, and then we had a Windows Embedded OS, Linux also. So if you use like Texas Instruments, Linux, I don't know what Linux they use, they have this tool to configure. The tool to configure the board support package. So when you open the tool, it says, I want to build a target application. What are things I want? I want USB, I check. I don't want Ethernet, I uncheck. And then I click build. Then you will build an image for that application. Okay. I'm not sure. Maybe one of you can answer this. I think Yocto Linux is the same thing, right? Yocto Linux is supported by Intel. It also has the same thing, right? You can build an image of Yocto depending on what you want and what you don't want. They have a configuration tool for that, right? Anyone can confirm. Let me type in the chat. It's called Yocto. Okay, so that's the kind of thing you have. Okay, IO device flexibility. Okay, so you can integrate many kind of different IO devices lah. Okay, I think that's pretty self-explanatory. Okay. Okay, what else? Protection mechanism. Okay, in embedded OS, perhaps you don't need much memory protection or sort of protection. Reason is because everything that's running on an embedded system is probably and most likely will only be your software. So if you have this router, and that is the Wi-Fi router, right, at home, that's actually an embedded system. Okay, and for this kind of system, only your OS is running and your system is running. So you don't expect anyone else to run anything on it. So it's pretty much safe. Okay, anything can go wrong will only be based on your program. Okay, if someone can hack the router, it's because you made it that way. Okay. Okay. What else? That's about protection. Direct use of interrupts. Interrupts means that things which need immediate attention. So you want to directly use them. And most of the time, these interrupts are time critical. So you want to make sure you have the least latency of processing this interrupt. So you need to have really fast interrupt. So on desktop operating system like Windows and Linux and Mac OS, there's no guarantee of this timing requirement. It will do its best so that you get a very good experience, but there's no guarantee that today you boot up your computer, it take 10 seconds, tomorrow it will be also 10 seconds. It could be longer tomorrow. I can't really guarantee that because I don't promise you that. Okay, I don't promise you that you're going to have the same level of experience. But on embedded, you have to make sure that that is actually achieved. Okay, otherwise the overall experience, overall performance, or overall quality of the system will be degraded. Okay, be degraded. Okay, moving a bit more. Other than that, you may have these characteristic as well. Using a general purpose OS you can use a normal operating system running on embedded, but you may have the following constraints. A normal operating system will require significantly more memory space, a lot more power consumption, and may not be able to achieve a real-time requirement. So using a normal Linux, not an embedded Linux, a normal Linux or a normal Windows on an embedded system can be done, yes, but you will have these problems. We use so much memory because it was never designed for this purpose. Okay. So how can I develop an OS, especially for embedded? So two approaches. One, take what you have and just adapt it for embedded. Or two, create a new OS from the scratch. Okay. Let's see. The first one is take an existing OS. So the common ones we have out there is Windows and Linux. The good thing is that familiar interface. Okay, and a lot of programmers out there that can program for Windows and Linux, so that's fantastic. But of course, it's going to be slower, less predictable. Okay, you'll not be able to meet real-time requirements. Uses a lot more resources, so maybe not a very good solution. So what we need to do is that we need to extend the OS by adding real-time capabilities. Okay, so you will have a Windows XP with real-time extension, or Linux with real-time extension, but not the whole OS is real-time. Only certain portion can run in real-time. Okay. The other one is actually why don't I create a new OS from scratch targeting embedded system? You can think about this, that when the first Android came, it was designed just for phone. So that's why the original Android, you can't plug in keyboard and mouse, and then you don't support, even today, I don't think so. You can use your, maybe you can. You can mirror your phone. You can plug your phone, right? I think Samsung got this DeX, I think. But I think you can mirror your phone. That's easily done. I have a 4-year-old phone, Samsung Galaxy S7. I can mirror it to my TV perfectly fine. But can you extend your screen? Which means what you see on your phone is different. What you see on your secondary screen is different. Extend. Perhaps you can't do that 5-6 years back. I don't know. Maybe the recent Android you can do that. But these things are more for desktop operating system. So the original Android phone does not support those things. The original Android OS does not support USB on the go. In other words, when you design a phone, when you design an OS for the phone, you never thought about, why would I want to plug in a pen drive to the phone? It doesn't make sense. Okay, a phone is not supposed to be plugged into a pen drive. Okay, but later, of course, they add that feature lah. Okay, maybe you want to copy some data, maybe you want to transfer something. So now I support OTG, things like that. Okay, so that OS was purposely designed for phone, and then later they add features. Now it makes it quite good already. But there are still things, limited things like multitasking. I think iOS doesn't have multitasking or split view before. I think now they have it. But if you look 5-6 years back, the iOS for the iPad, even though iPad is quite a big screen, right, 9-inch or 8, you can't do multitasking on it. You can't open two apps side by side because it was never designed for that purpose. But as you go into the future, then they start adding the features to have split screen and things like that. Okay, so these are purposely built OS for certain purpose. So for embedded OS, we build an OS which has very fast switching if you have multiple programs running. Real time, make sure it meets the deadline. Small size, so it uses very little memory. Respond to interrupt very quickly. Okay, and then minimizes how long the interrupts are being processed so that I can go back and do my regular tasks as fast as possible. Okay. Other than that, may have a fixed memory, may have a variable size partition of the memory, special operations for sequential files, so you can read and write to drive very quickly. Okay. For example, you have a digital single lens reflex camera, DSLR, and you want to take photo at a burst rate. Or even your phone also. My old phone, Samsung Galaxy S7, also got this burst mode. Okay, you press the button for capture and hold it, and then it will burst. But of course, it cannot burst forever lah, due to memory limitation and bandwidth. But you need to write the files very quickly. Okay, otherwise the burst mode will not be burst mode. Imagine you write a file and then you wait a few seconds, write the next file. It's not burst mode lah. Okay, burst mode has continuously very fast 12 megapixel photos. Okay, so for that you need to have a very fast I/O, special file ways of writing file. So those are the things you may want to consider for a desktop OS. Embedded OS. Okay, moving on. So I'll stop after another minute. Okay, other than that, you need to deal with timing constraint. Okay, provide bounded execution time for primitive. Primitive here means basic functions in the OS. For example, if I have a function, say create thread, or let's say a function called memory allocate, for example, that is a function or API available in my OS example. So I must guarantee a bounded execution time. That makes it a good embedded OS. What it means is that in my documentation, I clearly mentioned whenever you call memory allocate, it is guaranteed to complete in not more than 20 microseconds, for example. Okay, so this way, whenever I want to do overall system execution planning, that is, I want to know which task will run for how long, and so on and so on. So I can actually estimate already very accurately. My program uses memory allocate, my program uses fopen, so the total time in worst case, according to the documentation, is going to be 6 milliseconds, for example. So I really know because it will actually provide you with the maximum bounded execution time. So I guarantee you, it will always occur less than 20 microseconds. Worst case also 20 microseconds. So if you want to do some planning, take the worst case. You can already plan your scheduling in the system. Okay. Other than that, maintains a clock, real-time clock, provides special alarms and timeout, provides support for real-time thing like earliest deadline first, not just first come, first serve, but earliest deadline. Even though you came late, the task came late, but it has a earlier deadline, so it must be done first, and so on. Okay. Okay, so I'm going to pause here at this slide. Okay, so it has been 58 minutes. I'm going to see you in 5 minutes. Thank you. Okay, so welcome back after the break. Okay, so let's continue. So more theory in this chapter. So let's look at some of the popular OS we have for embedded applications. Some of the ones are maybe you have heard before, VxWorks, QNX, MicroC OS2 from Micrium, and some of the open source ones are eCOS, Embedded Linux, and so on. I'm going to show you a diagram later. Okay. By the way, you can hear me, right? Yes, I think you can hear me, right? You just confirm in the chat. Okay.
Yes.
Okay. So, of course, the OS will require a bootloader, right? So, OS like ECOS and embedded Linux are compiled as binary packages, and then to run the OS on an embedded platform, we need a firmware, which is called a bootloader. Okay, so this is used to load them from storage memory. Okay, so the bootloader also actually performs some sort of a low-level initialization. For example, initialization of processor, oscillators, SDRAM controller, and so on. So this is like the in your STM32 you have that the .s assembly file, right? What do you call that? Startup file, lah. Okay, something like that, right? So the bootloader is like that. So it's a firmware that is required to initialize the system before running. The same thing like your BIOS or what do you call it now? Not BIOS. We call it, it's a new name, UEFI. So those are also the same thing. Okay, there's a firmware that is required to initialize the platform before you actually hand over to the OS. So when you turn on your laptop, Dell laptop, and so on, Lenovo laptop, that firmware runs first, initializes the system, make sure RAM is there, make sure the hard drive is connected, everything is okay, make sure the password is okay. If you have a platform password, if you have TPM, or everything okay, then it hand over to Windows, and then you continue execution. Okay. So the common bootloaders are U-boot and also Red Boot. In addition to performing the loading of the OS, they also provide boot monitoring functions. Okay, so what is a boot monitoring program? It actually monitors or provides services for inspection of the platform, programming the onboard flash, and simple debugging. So um, you can always you can always update the firmware on your Dell laptop, right? Or if you have a phone, they always sometimes have a system update or platform update on the phone, which requires the phone to completely restart. Okay, so these things actually you need to have a program that allows it to flash itself. Okay, so when you're flashing the BIOS, you're actually replacing the BIOS, right? So there must be a program that allows you to flash the BIOS while in BIOS mode. Okay, so that's what the monitor program is about. So this is what I wanted to show to you. Okay, so um, this is the current trend in 2017. So this makes it 4 years old, right? But it's quite about right. Okay, so these are all the common operating systems used for embedded OS. Okay, just one second. Let me reply this message. Saya. Okay, so most of them they use this embedded Linux, a free real-time operating system. RTOS is real-time operating system. Some of them use an in-house custom operating system. Can you see any Tizen there? No Tizen, and I guess maybe in-house custom is Tizen. Android, a lot of applications are using Android. I guess smart TVs and so on. Again, Debian Linux, Ubuntu is also Linux. Windows embedded, still in the market. And then Texas Instruments, okay, Micrium, and so on. Okay, so there's a lot of different applications they use for as an embedded OS. Okay, what about this one? Please select all the operating systems you are considering using in the next 12 months. So a lot of actually, if you look here, embedded Linux, a lot of say maybe I should go for free RTOS. Okay, free RTOS, and then you see the diagram there. So what about Windows? From 8% down to 6%. People don't want to pay anymore, I guess. WinRiver is 4%, up to 4%, still the same. So a lot of them are trying to go for open source. Let's look at this one. Look at the diagram there, the top one. Can you see the arrow going up? What is the trend of using open source? So the purple color is actually the purple color. Let's look at this part. Okay, open source. So this is in 2012, 2013, 14, 15, 16, 17. 12, 13, 14, 15, 17 is a skip there. So it's the trend is going more towards open source. What about commercial is going down? So less people are actually trying to, or less people are what we call interested to do this. Okay, just one second. Just one second. Uh, Okay, sorry, boss asked something, so I have to reply. Okay. Can I pause for a while? I need to send a link. Is it okay? I'll be back in 3 minutes. Just let me just pause for a while. Okay, I'm back. So it just took me 2 minutes. Okay, coming back to this one. Okay, so you can see the trend, right? So I think free is good. Not only is good, but you must have a proper support for it, lah. So if it is free, you also need to make sure that there's a support in terms of community and so on. Okay. So what about my next embedded project will likely use? So it's a lot saying that I should be using, or I will be using, what we call open source, going up. What about commercial? Going down. Internally, also going down. So I think that because things are becoming more complex nowadays, spending times, hiring engineers and so on, so that you can build, you can purchase, or you can make your own built-in, in-built in-house OS is actually kind of expensive. I think probably the only motivation is probably for companies like Huawei, or those China companies which got sanctioned. Perhaps there's a good motivation for them to create their in-house. Otherwise, like this lah, you are now in the top in the market. Suddenly, some other country do not like you for whatever the reason is. Let's not go into the politics. But they sanction you, so they don't allow you to use their services. And now you have a problem. Okay, so maybe that's a good motivation to have in-house. Okay. So I always tell people and my students that you should always have your own technology, even though if it is not the best. Okay, so even if you can make your own chip, for example, Intel can make now 14 nanometers. Is that correct? Can you go? Are you down to 10 Intel, or still 14 nanometer plus plus? Anyone wants to say? Intel?
10.
Already 10, huh? Okay, so even if you can make your own chip, lah, let's say in Malaysia, and it's 14. And the market, Intel is at 10. I think AMD is using a different fab from a different company TSMC, I think is 5. Okay, fine. You are so far behind, 14 nanometer, but at least you have your own technology. People can't sanction you. Okay, you are free to do what you want to do, even though it's not the best. Okay, so that's very important to have something of your own. Now, that's the same thing. You store all your data on Dropbox, you store all your data on Google Drive, you store all your data on OneDrive, you use Gmail, you use Outlook. Suddenly you say, okay, Malaysia is a terrorist country, for example. And let's say, and they say, okay, we sanction all the services cannot use. So what will happen? All your emails are there, all your documents are there. Suddenly the next morning you wake up, you can't access everything. Example, in an extreme example. So if you have your own, at least it's not that worrying, even though it's not the best. Okay. Going forward, let's have a look at real-time operating system. Okay, so what is real-time? So real-time operating system comes from the definition of real-time operation. It means that defines the way the system works, reacts to events and interrupts, and schedules the system functions in real time and executes by following a plan to control latency and meet the deadlines. Wow, what a long term. What is latency? Latency is the waiting interval between instance at which a need to run the code arises and also start executing it. So that's a latency from the moment I trigger you to the moment you start actually doing the work. So that's latency. Okay. So let's look at a much simpler definition. A real-time system is one which the correctness is not only depend on the logical correctness, but also depends at what time it arrives. Okay, like I gave you an example just now. So if you meet the deadline, then a catastrophic failure may occur. Another definition, real-time operating system is the ability for the OS to provide required level of service in a bounded time. So it's about time. What about real-time? Okay, real-time does not mean speed, but keeping deadline. Okay, deadlines. Okay, what it means is that I have to meet a deadline that is I need to reach Penang by 6 p.m. today. Okay, by 6 p.m. because I have an event at 6. Okay, so I don't really have to drive as fast as possible and reach at 5 o'clock or reach at 4 o'clock, because it doesn't make any difference. The event will start at 6 regardless if I arrive early or not. Okay, if I arrive Penang by driving my car at 200 kilometers per hour and risking the safety of everyone on the road, including me, I'll arrive at 4 p.m. Okay, but it really doesn't matter because the event will start at 6 anyway. So it's not about speed, is just about keeping the deadline. So you just drive at the appropriate speed enough for you to arrive before the deadline. If 110 kilometers per hour allows you to arrive at 5:40 p.m. is good enough. You don't have to go faster. So what does it mean? It means that in a car, for example, you have an engine control unit that needs to do the timing for the oil mixture and so on. And in order to do all the calculation of all the sensor data and send a signal to the control to the actual car engine, okay, all can be done with just a 200 megahertz processor, and which means that you only need to buy a 200 megahertz processor. You don't have to buy a 1 gigahertz and tomorrow comes out a 2 gigahertz. You don't have to buy faster and faster because it really doesn't matter. You just need enough speed to keep the deadline, which is why you will see in most real-time systems, the processor is just cukup makan, okay, just enough to achieve the deadline. So how can we classify this? So what we have is on the left side is called non-real-time. For example, you have a circuit at Intel and you are simulating the circuit for 1 nanosecond. Okay, for 10 nanosecond, the circuit, you want to test the circuit for 10 nanosecond, you open your simulation tool, you open the simulation circuit, you press simulate, and then it will generate the result of timing and whatnot for 10 nanosecond. But the simulation will take 6 hours. You press run and then it runs on the back-end server and then you do something else. After 6 hours, you get back the results. That's non-real time. You're simulating a real-world event of 10 nanosecond. Okay, but it takes you 6 hours to do it. So that's non-real time. Okay, so it takes longer for you to do that. Okay, Muhammad Adib says 10 nanometer plus plus. Okay, that's for the earlier question. So coming back to that one, you know your movie, you watch your movie, right? Let's say Transformers. You watch a movie where the Transformer robots are fighting for, let's say, 1 minute. To render that 1 minute, it probably took them days and days to render that 3D graphics. So it takes a very long time to render it, and what you see on the movie screen is just for 1 minute. So that's non-real time. On the other side, if you're playing a 3D game, a Transformer 3D game on a computer where you're jumping the robot and going under the bridge and shooting something else and you see fire and so on, you want to see as it happens. When you shoot, you want to see what happens. When I jump over something, I want to see what it happens. I want to see as it goes. So that is real time. Okay. You can't shoot someone and wait for 2 minutes and then you see, oh, I missed the person. No, you want to see it at that moment. That's real time. Okay. In between, you have what we call soft real time. Now, soft real time is something like cruise control. So if you have a cruise control in your car, which I do, you can set the speed limit to 110 and then you can lift off your feet from the accelerator. So very tiring, right? Driving for hours and hours and pressing the accelerator at 110. Okay, if you follow the speed. So you can just set the car to 110 and then lift off your leg and then the car will drive continuously at 110. But as it goes up a hill, you will see it will not maintain 110. The speed will go down a bit, 109, 108, 105, 102, and then the engine will ramp up a little bit and it goes back to 110. And when you go down the hill, it will go a bit faster, 111, 113, 114, and then you can feel braking. And then you go down back to 110. So it will have a little bit of deviation here and there. You don't have to be really sharp at 110. A little bit off is okay. That's what we call soft. While hard deadline are things that cannot miss. Okay. So for example, an engine timing, right? If there's a misfiring of the engine, let's say it's from the control unit. The control unit is not sending the right signals. Maybe the control cables are not okay. So the wires, the power, the thick wires that goes to the injectors or going to the spark plugs are faulty. So you're having a misfire. You can really feel it. Even if misfire but a few 100 milliseconds, you can feel the engine is like having coughing. So it's not nice. Okay, so it's not nice. Okay, so that's called hard real time. Okay, same thing with video. If the video gets a little bit stuck, it's okay. You can tolerate, right? If you watch video, a little bit stuck, the video is a bit stuck, you can tolerate. But audio, you cannot tolerate. If the audio got a bit stuck, then you cannot tolerate, right? So that's the difference between our human processing. Some things we can tolerate. So definition, hard real time. If you miss a deadline, catastrophic. Things like airplane sensor, autopilot system, movement on the airplane, or those things, if it goes wrong, you want to yaw or pitch the plane and it responds later than it's required, then you can crash the plane. Soft real time, that if you miss a little bit, it's okay. For example, a little bit lag is okay. It's not catastrophic. You don't die. Okay. I mean, if your live EPL match a little bit delayed, you are not angry, right? Okay. Firm is another one. Firm is when you have a mixture of hard and soft. Okay. So what it means that if you miss the deadline, it will degrade the quality, but it will not be catastrophic. For example, I have you are not you lah. Let not say you. A person X is in the ICU unit at hospital Y. The person is on a ventilator system because of COVID-19. According to the requirement, okay. According to the requirement, Munim, is that the person needs to have, let's say, 10 breaths per minute. So the ventilator must press oxygen 10 times per minute lah. So push oxygen, after that withdraw, push oxygen. So let's say 10 times per minute. Okay, per minute is long. Do you breathe 10 times per minute? Does it make sense? Why not? 10 times every 6 seconds. Every 6 seconds you need to give oxygen to the person. So there's a hard requirement. So you must meet that 10 times per minute. But do you really have to be every 6 seconds? So there's a soft part for it. So you may pump the first one after 6 seconds, the second one after 5 seconds, the third one after 7 seconds, the fourth one after 6 seconds. So you may have a bit of deviation there. That is okay. So we call that soft real time. Okay, but the overall you have a hard requirement. But if you deviate anything in between it, as long as you meet the hard requirement, then the other requirement is considered soft. So we call that firm real time. So a quick example. Okay, so I will pick a person and you'll have to answer. Let me randomly pick. There's no random, it's a sorted list. So let me just choose. Lee Sun Chong. Lee Sun Chong. How are you? Are you there?
Hello. Yes.
Okay, quick question. Air France Flight 447 crashed into the ocean after a sensor malfunction caused a series of system errors. The pilots stalled the aircraft while responding to outdated instrument readings. Is this a hard, firm, or soft real time? $10 seconds? 5 seconds? 3 seconds? Give the answer and the reason.
Huh?
What do you think?
I think it's hard real time.
Okay, that's correct. So this is a hard real time system. Okay, thank you. Next one. Muhammad Najmuddin.
Yeah, I'm here.
Assalamualaikum, how are you? Good. Okay. Weather stations have many sensors for reading temperature, humidity, and wind speed, etc., etc. The reading should be taken and transmitted at regular intervals. Even though a sensor reading may be early or late compared with others, it can still be relevant as long as it is close enough. Is this hard, firm, or soft?
Soft.
Correct. So this is a soft real-time system. Easy, huh? Easy, huh? Okay. Next one. Let's go down. I don't know. Prashana. Sorry, Prashan, since you always ask questions, so you're an easy target. Okay, just joking. Mars Pathfinder spacecraft. Before that, let me just confirm. Najmuddin, which sections are you from?
Section 5.
Munim section. Okay, before that, Lee Sun Chong, which section are you from?
Yeah, section 5.
5 also. Okay, Prashant, section 5 also. Prashant, are you there? Hello?
Still alive, maybe.
Maybe it's pretending his microphone not working, so he doesn't have to answer the question. Prashant, just joking. Okay, ask it. I said what? Help. See, Prashant don't want to answer the question, so he's pretending. Suddenly today, microphone not working. Just joking. Never mind. Okay. Let's ask my student, Janice. How are you? Janice, are you there? Okay. Yes, okay. Mars Pathfinder spacecraft was nearly lost when a priority inversion caused system restarts. A higher priority task was not completed on time due to being blocked by a lower priority task. The problem was corrected and the spacecraft landed successfully. Is this a hard, firm, or soft real time? Take your time to think.
Firm.
Yeah? I can't hear you.
Firm real time.
Firm real time. No, actually, this is a hard real time problem. Okay, but close enough. Firm real time is close enough. Okay, but it's a hard real time problem. Okay, next one. Anybody wants to volunteer? Let's see, volunteerism. Don't worry lah, salah pun tak apa. Okay. Piamuni, you want to choose anyone? Zeng. Okay lah, so Zeng Yu Tan. Okay, Zeng Yu Tan. Okay, so this is a question for you. Are you there?
Can you be right back?
Be right back. Okay, okay. Okay, so I always tell my wife, you know, if you want to give names to your children, don't give from A, don't give from Z. Because if you go to school, they're going to get called first. Okay, so give some random name in between. Okay, don't give A or one. Okay, okay. Shasha Farina. Are you there? Yes, okay. Okay, a manufacturing system with robot assembly lines, okay, where missing a deadline results in improperly assembling a part. As long as ruined parts are infrequent enough to be caught by quality control and not too costly, then production continues. Is this hard, firm, or soft?
Maybe firm.
No, this is actually a firm real time. Why? Because you have this requirement that, okay, as long as you don't get a very good, as long as you miss, you know, it's not a properly assembled part, it's okay, as long as the QC doesn't catch it. Okay, so the QC is the hard part, this assembling part is the soft part, so you have these two requirements. As long as no one detects it, we just proceed, so it's firm. Okay, I'm running out of ideas.
I think she answered firm.
Again?
I think she answered firm.
Oh, she answered firm. Oh, I heard soft. Okay, so my mistake then is firm. Okay, that's correct. Okay, my mistake, maybe I didn't hear it properly. Any other name? Munim Zabidi is okay. No, she's just joking.
Okay,
Okay. No. Let the students, let them wake up. Let them wake up.
If I fail, then I don't have to teach for the rest of the semester.
You know, Munim, this is the last day of the semester for them. So either way, you have to teach. Okay, Khairil Anwar. Okay, Khairil Anwar. Okay, are you there?
Yes, I'm here.
Okay, so a quick one. A digital cable set-top box such as Astro decodes timestamps for when frames must appear on the screen. Since the frames are time order sensitive, a missed deadline will cause jitter, diminishing the quality of service. If the missed frame later becomes available, it will only cause more jitter to be displayed, so it's useless. The viewer can still enjoy the program if jitter doesn't occur too often. Is this hard, firm, or soft?
Soft real time.
Okay, it's actually firm. Okay, it's actually firm. Okay, so as long as you miss once in a while, it's okay. But if you miss too much, then it becomes useless. Okay, you will not enjoy your Astro transmission. So this is actually firm. Okay, a bit tricky, huh? Okay, a bit tricky. So is this the last one? No, I got two more. I'm running out of ideas. There are 51 students, but I don't know who to pick. Piamunim, who do you want to pick? Okay lah, Prashan lah. Okay, Prashan, you answer from the chat. Okay. A video game console runs software for a game engine. There are many resources that must be shared between its tasks. Okay. At the same time, task needs to be completed according to the schedule for the game to play correctly. Okay. As long as tasks are being completed relatively on time, the game will be enjoyable, and if not, it may lag only a bit. Okay, so is this firm or what? So Prashant says firm. This is actually soft because there's no hard requirement here. So this is kind of tricky also, but this is actually firm. This is the final one. Okay. So I think I also don't know lah.
The last question is firm or soft. You said soft as first, then you said firm later.
Firm. It's firm.
Firm. Okay.
Nobody wants to play a game with 10 millisecond or longer lag. Okay. Okay, so I don't game, so it doesn't matter. But yeah, you're right. Okay. Okay, Zeng Yutan is back. So Zeng, just to check that your back is not a bot typing there. So why don't you answer the final question? Simply is either hard, firm, or soft. An inkjet printer has a print head with control software for depositing the correct amount of ink onto a specific part of the paper. If a deadline is missed, then the print job is ruined. Zhang Yutan, is it hard and so on? Can you speak, Zhang? Do you have a microphone? We want to hear your voice. That would be nice. Do you have a microphone? No? No, okay, well, then I just read your chat lah. It says hard, and you are right, missing the, because printer runs very fast, right? Especially inkjet, right? So if it misses the positioning, then paper becomes, then the output is wrong lah. Okay, then you cannot undo the output some more. Anything is already on the paper, it's already rosak lah. Okay, so I hope you get some idea about soft, hard, and firm deadlines, a real-time system. Okay, let's continue. What's a real-time OS? So in time-critical embedded OS, a normal OS may not able to meet the time requirements. So we need a special OS for that, and we call that RTOS, okay? Or real-time operating system. So it is designed such a way so that it is able to meet the deadline. So the real-time response is basically achieved by allowing the suspension of lower priority tasks while allowing higher priority tasks to be processed when they arrive. So this is why I mentioned earlier you need to have this preemptive OS. Okay, so to have an RTOS, you need to be preemptive. Okay, not preventive, preemptive. Okay, so it allows you to, and it enables you to execute concurrent processes or thread, and it also allows you or provides you with a mechanism to let processor run each process per scheduling, and also set the rules during execution that allows processors to be able to finish its task in the assigned time interval. Okay, and also priority. Okay, so some of the features of RTOS: determinism and preemptive. So we talked about preemptive before. Determinism means the variation of the best case and worst case response timing for the same event. So this way we know, like I mentioned earlier, you have this bounded time for the primitive functions, right? So we know that in the worst case, how long does it take to compute? Okay, so RTOS is talking about time, right? So we want to know in the worst case, what kind of scenario, in the worst case, what kind of time is going to consume. So based on that, I can do the scheduling. So that's very important. Okay. Another thing is interrupt latency. I also talked about this earlier. So the time taken to service an interrupt depends on how the OS manages the interrupt exception. Okay, so there's a sentence down there. For example, in older ARM version 7, we have the fast interrupt. Okay, so that is to reduce that time. Okay, so we want to reduce the latency time from the moment you are triggered to do something to the moment you start actually processing it. So because we want it to be really, really fast, especially for those tasks which are high priority. Okay, we don't want the task to wait too long. Okay. In some application, you may have multi-rate. Multi-rate means that different things that are running on the system may have different rates of processing. So if you have audio, you have different rate. Video, you have a different rate. Network data, different rate. So a real-time operating system may also need to cater for this kind of problems. So we have some sort of what we call a pure real-time. So this pure real-time is designed from the ground up to be made as a real-time OS. So from the first day when it was designed, the person was already having in his mind that I'm designing a real-time OS. So from the beginning, it was already geared towards that. So it is a completely real-time compliant. Okay, the advantage is little or no overhead. An example of them are eCOS, Nucleus, PSOS, VxWorks, and so on. The rest of the things you can read from the slide. Nothing much there. What we have also, like I mentioned before, extensions. I talked about Windows with extension, Linux with extension. The thing is that you don't get the whole OS as real-time. Only certain portion will be real-time. Okay, so that's the term there. No general real-time ability. But again, general purpose OS is large, so your computing and memory requirements are also quite big compared to the purposely built real-time OS. So let's have a look at the different types of kernel. So we talked about kernel earlier. There's a core of the OS where scheduling and time management and memory management is done. So we have two kinds. One is a monolithic. This one is all the services inside the kernel. If you want to modify, you have to rebuild the kernel. Okay, but the advantage is going to be faster lah. Okay, because there's not much overhead. Disadvantage is that everything is integrated, which is not necessarily a good thing. If you need to remove something, you have to rebuild the kernel. In microkernel is it may have a bit more overhead, but the what we call the non-essential functions are on separate or outside the kernel. Only the essential things are inside the kernel, such as virtual memory allocation, resource management, scheduling. Those are inside the kernel. Other functions are outside. So this gives you a lot more flexibility in the OS. Okay, so that comes to this one. Okay, so if you've read a little bit on Huawei's Harmony OS, so this is the one, the news on 9th of August. I think during this time, it was at the height of what we call Trump and the sanction on China, and don't allow them to use Android, and doesn't allow them to use what we call Google services. So they had to come up with their own OS. I haven't seen it yet in the market. Okay, so but they say, okay, Huawei launches new distributed operating system called Harmony OS. So you can read that. There's a lot of things there. But it's written there in one sentence. Harmony OS is completely different from Android and iOS. It is a microkernel based distributed OS that delivers a smooth experience across all scenarios, and blah, 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 other marketing thing lah. Okay. These kind of things you read from marketing people lah. Okay. Intel also got a lot of marketing thing, right? Okay. Microkernel based. So this is where I think you can relate this information with actual product in the market. Okay. Now, what are the components of RTOS? Okay, so we have the task management, including scheduler, synchronization, memory management, interrupt routine mechanisms, I/O management, the HAL, hardware abstraction layer, the development environment, that is like ST-Cube MX, ST-Cube IDE, the GCC compilers, communication subsystem, maybe you need 4G, 3G, 5G, those things, and also board support packages, microcontroller support packages. Those are everything we need in an RTOS. Okay, we need all of these things, then you have a good experience in developing it. Imagine nothing for ST-Cube, just a PDF file, 453 pages PDF file describing all the IOs inside STM32F446RE, let's say. No compiler for you, no CubeMX for you, no debugger for you. Go open a notepad and compile yourself. Imagine that. So no one will buy that chip. Okay. So what happens in when you have the CPU allocation while doing task management? So we have a thread. PM Munim is going to talk about thread in the later slide this afternoon. But like I mentioned, thread is a unit of task, okay, independent unit of task, okay, running in a program. So you create a thread, and then it gets dispatched, and then it runs on the system. Okay, so if you open your task manager, you can see a lot of threads running. So maybe I can show that quick one. So let's say we have a task manager. To hide things on my desktop, I just double click this. Okay, so that's I can see a lot of programs running, right? So you go on the performance, on the details. So these are all the processes. So we call that processes. Okay, and I can put here, right click here, select columns, and you can see here number of threads. And you can see these are the threads running on my system. So if you look at Cisco Web Start, 13 threads running in it. In my system, I have 3,300 threads running. Okay, some are awake, some are suspended, some are sleeping, some are running. Okay, some are getting started, some are getting destroyed. So it goes up and down. And these are the handles. So remember, we talked about handle when we were programming the STM32 yesterday, right? We have a handle to the ADC. We have a handle to the UART. We have a handle to blah blah blah. Okay, I2S. Okay, so you have handle is the way you hold to something. So on Windows, you have handle to everything. Handle to a file, handle to the device context, the one I'm drawing on the screen, handle to window, H window, handle to window. So everything got handles, got a lot of handles here. Okay, and maybe I can show one more thing here. I can right click on, let's say, Cisco Web Start here, and right click, and you can see here got priority. So we remember we talked about priority, task got priorities, right? So now it's normal. So Windows tries its best to allocate same time quantum for this with other things, but I can push it to real time. So this way, Windows will give more time to Cisco. But of course, Windows is not real-time OS, so it will not guarantee that. But it will try to give more time for this guy. Okay, so other things will become slower in the background. Okay, so if you're rendering a file, you can give low priority to antivirus and so on, and give high real time to your renderer. Then you get done work faster. What else? Remember we talked about multiprocessor. You can also set here. So I can say this Cisco WebEx Start runs on all processors, it says, which means Windows has the flexibility to schedule as it desires. It's not that it's running all 7 or all 8. It is free to assign. Okay, but I can say no, only assign to CPU 0 only. I can do that, but don't do that. If you have no reason, don't do that. But those are some of the things you can see here. Okay. So as you can see here, these are the threads running. So let's see programs with single thread. Can I sort that? Single-threaded programs such as Wacom host, that is my pen and tablet. Wave, this is for playing audio on my computer. I have a Java update scheduler, single-threaded. What about those who are running a lot more threads? System is having 236 threads because you have a lot of things running on the system. My antivirus got 78 threads. Oh my God. And then my Cisco having 64 threads. And so on. But not all threads are running. Some are suspended and some are just waiting for some event. Okay, so coming back to this one. Just 1 second. So you have a thread, it gets scheduled and dispatched, and then it runs. One, it completes, it starts, it gets terminated. Otherwise, sometimes it's running, it's requiring a resource, and the resource is can't be used, so it gets blocked. Once the resource is released, it can capture the resource and then it can use the resource. So sometimes you're trying to open a file and it gets locked. Okay, and then you can't open the file. So it's just say try again. Do you want to open the file? Try again, try again. So once the file has been unlocked, then you can press try again, just proceed. Okay, right? So in the background, it's the same thing like that. Threads are actually sharing data. So once the data is being locked, we call that critical section, which means only one thread can go in and do something. So once you get locked, other threads get suspended, pending. Once it get released, then you can capture the resource and continue execution. Okay. Termination is where you see just now in my task manager, sometimes threads go up, sometimes the threads go down. That's the threads are being created and destroyed, created and destroyed. I do not know who is doing that because there are so many things running on the system. Okay. So a quick diagram here. So this one is just showing the scheduling process lah. Okay, so you have context switching, you have process state. Okay, so some processes are dormant. Sorry. Okay, some tasks are actually dormant. Okay, some actually are waiting for some events, so they are what we call sleeping. Some are running, some are locking, waiting for some tasks. So there's a process running here. Sometimes you're creating, sometimes you're deleting what we call tasks or threads. Of course, like we mentioned about, we got a lot of scheduling techniques. Okay, first come, first serve, shorted job, first scheduling, priority scheduling, the one that's important, or round robin. So we have different ones. And this is also good lah. Shortest job, first scheduling. So this one is nothing to do with this one. I'm just telling you in general. Sometimes I was reading a book lah. So it says that you have so many things to do in life, right? You have want to do this task, you want to wash your car, you want to do your work, and you look at your list, you got 10 things to do. So you get demotivated. So they say that what you do is you do the shortest job first. Okay, what it means is that try to cut down the list that will motivate you. So even though the thing is not so important, like doing the dishes or washing your clothes or filling up petrol to your car inside your car and then doing your work. So when you see you do the things which are simpler first, those are not really important, but when you do that, your list becomes shorter and you feel more motivated. So that's one way of motivating yourself. Nothing to do with this, but just telling you that. Okay. Okay, so memory management, that's very important for OS. So the diagram on the right is just simply showing that a process, the OS is, loading things into 1 megabyte fixed memory sizes. But the main point is that whenever you request memory from the system, it goes to the OS, then the OS allocates it for you and returns you the address of that memory. Okay. It also makes sure there are safeguards so that other programs do not overwrite your memory. Also safeguards that when you have a stack and so on, they'll keep a little bit of buffer so that if you overrun your stack or buffer, it can trace that, but it will not crash your program. So those are some of the things done by the memory management. Interrupts and traps. Okay, so we need interrupts. Okay, what are the application for it? Process management. Remember, we want to switch between programs. Okay, we can do that using interrupt. Okay, a fixed interrupt. Also, your device management. Okay, such as keyboard input, DMA, all those. When they complete, they need to interrupt the CPU to tell that, okay, I've done it. Okay. We also have things like trap. Trap means errors, exception. Okay, exception. So things like when you do some processing, you may get overflow, underflow that you can generate exception. Or sometimes you can create a trap on purpose. Okay. That is, we are creating an exception on purpose. Exception means not going the right way, or it's not what you expect. Okay, exception means trying to divide over 0, or trying to write to a file, the file no longer exists there. So those things are exceptions. So we can also create our own exception, or we also can create our own trap, such as supervisor control. This is one way in our instruction where we can transfer the control back to the OS. Okay, or when you write your program, right, you put a debug point in your compiler or in your IDE, right? You're actually adding an exception there. So when the program runs and hits that line, it actually causes an exception. So it goes to the debug handler, for example. Okay. So let's see this priority inversion. Okay. So this one is a long explanation. Okay, so can you look at this diagram, or you have printed this, and read the next slide? Okay, so Nick, the next slide. Okay, so I will read the next slide while you look at this slide. Okay, so the problem is this one. The problem in this slide is this one. This is the order of a priority. Okay, job 1, job 2, job 3. This one has the highest priority. This is a very important job. This is the lowest priority job, and this is time. So in this problem as well, what you can see here is that they don't appear at the same time. Sometimes the higher priority comes later. And that's number 2. Okay, so number 1, you can see the priority. Number 2, you can see that time is going this way. Number 3, you can see that important tasks may not come earlier. You know, in life, something important may come at the very last moment. Okay. Today you want to submit the assignment, suddenly something else happens, even worse. Okay. That needs more attention. Okay. So they don't come at the right time. They always come at the wrong time. So that's number 3 is trying to show in this diagram. Number 4 is that, some tasks, they are using normal execution. And sometimes they're using a shared resource where only they can use. So we call that critical section, critical section. So when you are doing this one, only when you see this gray area, right? This is where this particular job is accessing a resource that only he can access at this particular moment. Other people cannot access it. So if I want to access the resource here, then it is not allowed because J3 is locking it. So in this example, what's actually is being demonstrated here is this. What happened is that job 3 is doing its normal work because it started first. Then at time 1, it started to do something on a shared resource. Okay, and then that's okay, fine, no one is using it. And at time 2, job 1 is, has a higher priority, arrives. So when job 1 arrives, so we switch and do job 1. Okay, because it has a high priority. Then at time 3, job 1 wants to access something that has been locked by J3. This A here is currently being locked by J3. Then I switch to J1, and J1 wants to access A, but it is currently locked. Okay, because this guy is using it before being preempted. So what happens here is that I have to let J3 complete first. So I let J3 complete first, finish. Then after J3 completes, suddenly J2 comes. So J2 has a higher priority than J3. Oh, sorry, J3 not completed yet. J3 just executing. I need to clear this so that I can unlock it, release it, so J1 can use it. But before this guy finish, suddenly J2 comes. So J2 has higher priority than this guy, right? So it switches to J2. At the same time, we are forgetting that J1 is actually waiting for this and is being held up too long. So J2 runs, and J2 is not using any critical section. He's using his own data only, not using A. So when J2 finishes, I go back to J3, completes the critical section, then releases it to J1, and J1 is being is being held for too long. It's been held for too long. So in this case, at this moment, it seems that J2 is more important than J3, when in fact J1 is the most important. So we call it inversion. Okay, so there's an issue there, right? So you can read that lah. I copy paste from that documentation. I just formatted a bit lah. Okay, so you read yourself in your free time, but that's the issue lah. What about is the solution? Okay, we can do inheritance. Inheritance means that when I switch to this guy, okay, and then this guy wants to read the critical section, right? But it's locked, right? So then at this moment, I go back to J3, and then I continue executing J3. Okay, so J2 arrives here, but I do not allow J2 to run because J3 is currently having the priority as it is J1. So at this moment, J3 is like J1. So it has inherited the priority of J1. So when J2 comes here, it wants to execute J2 here, like in the previous slide. I don't allow you because I got higher priority than you because I have inherited the priority of this guy. So no, you push you back. So let me complete this guy. So when I complete this guy, then I release it back to J1. J1 completes it, then goes to J2 and continue. Okay, so we call that priority inheritance. Okay, and you can read this in your free time. Okay, same thing lah. Okay, so let me just continue until the end. Okay, so at 11:20 there's no break. Just a little bit more slides and just go quickly. Okay, so I've also talked about this before. API, all the things you see in your HAL, right? Those are all hardware abstraction layer. And the functions you have to talk to the hardware is like API lah, application programming interface. So any application that talks to the hardware using the same API, even if you change the hardware underneath, as long as the API is there, it will work fine. Okay, so the API is your contract lah, is your contract. So whenever you write a program for, let's say, Windows, you write a program against Windows 10 API. Okay, so as long as Windows 10 maintains the API, so your program will run fine. Which is why older programs from 10 years back, you can still run on Windows 10. The reason is because Microsoft has not removed the API yet. Although it's not safe or it's no longer required or better API is now available, but to maintain compatibility, I do not deprecate that API, I still maintain it. And probably they put a remark there, okay, this will be removed in future version, for example. In future version of Windows Server, this will no longer be available, okay, for example. Okay, so that's API. So normal APIs are process management, memory management, file creation, I/O. So those are normally, we have APIs lah. Okay, so some standard you need to fulfill for RTOS. Okay, some of the features you need in RTOS, asynchronous, semaphores, message queue, a lot of things here. So I'm not going to cover all of this, just introduction. Okay. POSIX is another system, portable OS interface for Unix. Okay, it's a family of standards specified by IEEE for maintaining compatibility between Unix OS. There are actually several versions of POSIX, but the latest one or the important ones are POSIX 1 and 2. It allows you the code portability. So if you write a program against POSIX, and then you know that anywhere where the compiler or the library support the same POSIX, then you guarantee you can compile it, no problem. This is a diagram just to show you different operating system will have a different code size. Okay, so some are larger, some are smaller in terms of code size. So it depends on what you want to do. Okay, we talk about this. This is what we call footprint. Okay, you have this memory footprint and you also have the disk footprint. Disk footprint means how much space you need to install the OS. Okay, and the other one is memory footprint. Once it starts running, how much memory it needs to run. Okay, so you have to have both. You don't want an OS that takes so much disk space, and also when it runs, also takes so much memory space. You don't want that. Okay, so scheduling. So we have priority base. Okay, we have based on priority. The one with the high priority will get more time. Okay, the one with the lower priority will get lower time. So it is round robin plus priority. Could be like that. Round robin means I go one by one. Okay, so you can imagine this like in a class, you have 20 students, standard one. Okay, standard one in Malaysia, let's say, a 7-year-old student, have 20 students in the class. So as a good teacher and a teacher that is fair, Adil, right? I should give same amount of time to everyone. So if I want to teach ABC, I should give every student 10 minutes, face to face, one to one. Okay, I teach ABC. That would be fair, right? But actually, that is really not fair. Okay, fair is not giving all my students A. Okay, all my 51 students, including PM Munim section, I give all of you A plus. Are you happy? Yes, you are happy. Is that fair? That is not fair. Fair is depend on how much effort you put, then you get A or B. That is fair. Although getting an A is a good thing, but a person who did B plus quality work but got an A, he's happy. But a person who did an A plus quality work and got an A is unhappy. Why did I just get an A? Why did he get an A? He didn't do that kind of work. So it's not fair. So in class also the same thing, right? So even if you have 20 students, you're going to give 10 minutes per student. That's not fair. There will be students who are weaker, who never went to kindergarten, who from the poor family, who never seen ABC. You should give them more time. In other words, you should give them higher priority. So you'll be going one by one to every student in a round robin fashion, but you have extra what we call property called priority, and you mark the property on that. So now the schedule will have round robin plus priority. Okay, so things which have high priority will be get longer time to be able to process its tasks, and things with lower priority will get shorter time, but we will still cycle through them. Okay, so those are some complex scheduling things lah. Okay, so sometimes you also have a priority increment. What it means is that a task with a 0 to 255 priority, okay, 0 highest, 255 lowest. Let me give you an example. Don't read that one. Let me give you an example where high priority is 10, low priority is 0. Let me give you this example, okay? So I imagine I have a task with 1 priority and another task with 7 priority. So the 7 will get a lot of time to execute, 1 will get very little time to execute. So what will happen is that the 1 will take extremely long time to complete. So some scheduler algorithms will increase the priority over time. So in the first cycle, the priority is 1. In the second cycle, the priority becomes 2. The second priority becomes 3, 4, 5, 6, 7. So it will get more and more time. Once it reaches 7, then it becomes go back to 1. So yeah, I will increase the priority a little bit. So it will not like it will not look like it will take forever to complete. Okay, you'll get a little bit of increment in priority and then decrement back to the original priority. So those are all scheduling algorithm. So I'm not really expert in that. I guess there's a special topic on how to write OS, but I hope you get the idea what is scheduling and priority based, and all of this requires a preemptive preemption. Okay. Okay, ISR. So interrupt subroutine code. This is where you want to, what is this? With with interrupts, the system is in form of external events. So if you have any external event, you can tell the system using this interrupt. So it's another portion of the code which is not linearly in your main function. So if you see your code, you'll have some variable declaration, you have your main program, and then you have a while loop in it. You will not see the interrupt subroutine inside that while loop. The interrupt subroutine or the interrupt function is outside. How can I call something outside from my while loop? So that's where the interrupt comes in. So when it interrupts the CPU will change it to ISR handling. So it will context switch to ISR. Okay. So even though you're not calling it from your while loop, it actually can be accessed from outside. Okay, from outside. So that's how ISR works. Okay. Of course, you have to do some dirty job lah. Like you have to, handle the context. Okay, anything you locking and unlocking is all your responsibility lah. Okay. Another important thing to mention is re-entrancy. So sometimes you have a function that you may be using. Let's say you have a function X. Okay, and then your program is calling this function X. Okay, and let's say happen to be inside your function X, you have a variable, static variable Y, which is a counter. Let's say a counter. Okay, so what can happen is that the main program A could call function X again and again before it completes. So I'm halfway doing this, and then A is being called again. A calls function X again, or maybe another task is calling function X again. While the original call for function X is not complete yet, So you may be entering the same function multiple times even before the function completes. So we call that re-entrant. Okay, so we have to make sure that if the function is using some variables, or if you're using some global, or if you're using some static variables inside the function, you have to be careful that because the next call, even if this is not complete, the next call is going to use the same static variable which has already been used by the first call that has not completed yet. So that may result in incorrect operation. So I'm calling function x and I set c to 10. And then I'm doing a few lines of function x. And before I complete function x, another person called function x and re-enters that. And it will use that 10 right away. Okay. From the go start, it uses the 10, which is not right. And then it modifies that 10 to 99. And then the other function is now using a 10 or 99. So now there's a problem there. So re-entrant code, you must make sure that you handle these kind of issues. Okay. So this is just a demonstration of that. So you have a common function that different tasks are using it. To make sure the code is a re-entrant, you have to make sure that when you use static variables and use global variables, what's going to be the state if you did not complete the function and it's being called again. Okay. So you may want to put these guarded globals, okay, mutual exclusion mechanism like critical sections, okay, which means that when you reach a certain part of your program, okay, this is function x in a certain point, let's say a global variable is a. Don't say var lah. Okay, var is C++, so a. Okay, so at this part, you're modifying that a as a global variable. So you want to start a critical section and critical section here. Okay, so if another person calls fx, if the critical section is you are inside the critical section, then it will get blocked here. So only one person can update this. So this is for synchronization mechanism. Okay, but this is not a good way. Okay, you can't avoid it sometimes, but it's not a good way. Why? Because this for multitask environment, for multi-core environments, when you have this kind of critical section, your program, which is now parallel, many things running at the same time, when this guy creates a critical section on the variable a, he creates a critical section, then everybody now becomes serial. Everybody now becomes serial. And then after the critical section has been released, then you become parallel again. So we are introducing serial portion in a parallel code, which creates a bottleneck and reduces your performance. So we want to avoid critical sections, but sometimes you can't do it away with it. But the effect is that it will reduce the performance of the program. Okay. Okay, so intertask communication. This one I talked about earlier, right? Remember, we have many processes. You want to talk across the processes. You may want to create pipes. You want to create sockets. You want to do remote procedure call. So these are some of the ways, okay? The simplest one is copy paste. Copy to clipboard, paste to another one. That's a communication from one process to the other. Okay. If you want to talk within the same, Prashant is asking, is exception and trap the same thing? Well, exception is general, and then you can break into software-based exception. We call it traps, and then we can call it hardware-based exception. We call it interrupts. Okay, so you can divide it into that way. So generally, we just call it exception. Okay. If I'm wrong, I think Pemunim can correct me on that. Okay. Please note, I'm not so expert in these things, so I'll try my best. Okay. Okay, so intertask, so we talk about intertask, how you communicate between this. I do not know, have you seen this on Windows or not? We call it OLE. Object linking and embedding. Piamuni wants to say something? Yes, Piamuni, want to say something? No, okay. Have you seen object linking and embedding this on Windows? This is where, I don't know in the latest Windows got or not, but older Windows, what you have is you have Microsoft Word, and then you copy something from this, let's say a diagram. Okay, and then I think it's still there, and then you paste.
Yeah, still there, but not push, not in front. They don't push it.
They don't push it the name, right? So when you paste this Excel in the Microsoft Word, it's still an Excel, and you double click this, it opens Excel.
I think if you paste Visio in if you put Visio graphic in PowerPoint, you double click it, you will open in Visio. I think it still happens.
Yes, it still happens. So you can paste a thing as picture, then it becomes just a picture, or just paste it. It doesn't say like PM Munim said last time when you save, paste it, it says save as OLE object. Paste as OLE object. Now I think it doesn't say PM Munim is right. So that is actually intertask lah. Intertask. So you're actually having this kind of connection between one and another program. Okay. This is a problem of sharing data. Okay, so I don't know. I like to give this example. So let's say this is Penang. Okay, and let's say this is JB. Okay, okay. So at 10 a.m., the amount on my bank account is 1,000. Okay, at 10 a.m. At 10:01, 10:01. Okay, someone is depositing money in my bank account 500. At the same time, I'm actually using an ATM machine to withdraw 500. So what is my final sum in my bank account? Okay, anyone can answer this? So of course, humans, they calculate in steps, right? 1,000 plus 500, 1,005, 1,005 minus 500, you get 500, right? Okay, sorry, you get 1,000. Sorry, my math. Okay, but in reality, it's not like that, right? It's like you read a variable A, which is 1,000. This is a variable A. So in the first part, the Penang part, you read the variable A, and you do this A equals to A plus 500. So this A is a copy, that's 1,000. And in JB, you're reading the same variable A, and you're doing A equals to A minus 500. And then you have this in consistent state, right? So this is a copy of the variable being used before updating to the primary variable. Okay, so there must be a way to synchronize these two things. Okay, so I always like to give this example, even if this is a correct example or not. So if you have a shared data and everyone is, if you're reading, not a problem. But if one of the person is trying to do a write, then you have this race condition. Okay. So you need to have this, in software, you have to have a method. In hardware, we have that instruction, right? On the ARM processor. What's the instruction? I forgot in one of the slides. That allows you to do atomic operation, which means that that operation will complete in one operation. So you have a consistent state, atomic operation. In software, you can have these locks and so on. Okay.
They don't have it anymore. ARM7, they have a special instruction. For Cortex, you just use bit bending.
Okay, that is for bit bending. For bit bending, you can do that. Then make a copy, change it, and then something will change in between. Might as well use bit bending. Okay. Semaphores. Okay, this is all the things to do that thing. Okay. Basically, it's like a baton. Baton, baton. You run on a 4x4 and on the track, right? You hand over the baton. Whoever got the baton, he got the controller. So this is something like that. So when you want to do something, you have a baton. Okay, so the baton, you hold the baton, so only you got the control to that particular thing. Okay, after you finish, you hand over the baton to someone else or return it back to the system. Okay, more than that, in Windows, you have a lot of this. This is for counting. So how does Windows knows that you can release the memory? So if I want to track every memory allocation, that would be very difficult. Okay, so what Windows do is that it has a counter. So when you, example, I open a handle to a file. Okay, so this is it's done a lot in garbage collection. For example, Java, C#. Okay, so I have a handle to a file on my drive. I open a file on my drive, C, desktop, PowerPoint.exe, PowerPoint.ppt. I open a file and I got a handle to the file. Okay, and I do not close the handle, and I use this file handle, F handle, a lot of places in my program, in a thread number 1, in a thread number 2, and so on. How do I know that the automated garbage collection can release the handle and is no longer in use? Okay, so how do I know that? So whenever I capture the handle, it will actually increase the count. So whenever the count goes to 0, I can actually release the file automatically. So garbage collection will kick in and clean up that allocation of the file in the memory. So that's one way where you use a counter to trace something. So in this one, the example says that, okay, whenever you have, every time a semaphore is given, you increase the count. if the count becomes 0, then a task that is blocked to take the semaphore is given the semaphore and the count is increased. So this is one way or simple way of what we call checking who is using something, and if someone is blocked, it's not being released to it until the count becomes 0. So just a simple algorithm or simple method of handling this thing. Okay, so final slide. Okay, so intertask communication message queue. So allows a variable of messages to be queued. Any task or ISI can send a message to the queue. Multiple tasks can send and receive the message from the queue and so on. So this is also interesting. This reminds me of Windows again. Sorry, I use a lot of programming on Windows. So in Windows, all your UI messages actually goes inside a queue. Okay, so whenever you press a button OK, it generates a Windows message, button clicked. So that's a queue, goes into the queue. Whenever you move your mouse, it draws a screen. So it says Windows message, DC update, device context update. So it goes inside the queue. So in Windows, we have a message queue. So all the messages goes inside the queue. So this is a button click screen update. And then the message pump, okay, is a while loop, picks the thing from the queue and handles it and so on. Okay, so that's for every application. There's one message queue, makes the application single-threaded UI. Okay, so the UI is single-threaded. What it means is that if I click a button and the button is opening a large zip file, 60 gigabyte zip file, and it's taking very long time, then you see the Windows UI for this single-threaded program cannot update the screen, because the update screen is now queued at the back and this message has not been processed. It got queued and blocked. So when this happens on Windows, on older applications, you will see you click a button on the simulator or something, click OK or run, and then the whole thing waiting for this button run, and then you try to move the window and then it will say simulator in the bracket not responding. Okay. Oh, after some time, okay, everything okay again, because this thing got cleared and then the rest of the queue start jalan. Okay. But while this is blocking for 2 minutes or blocking for 10 seconds, that's a long time in computer, right? 10 seconds, right? Especially UI, then it becomes not responding. What not responding? Not responding to the message queue. New message queue is jammed. Not saying the program crashed. Okay, maybe crashed, but it's jammed. So this is a queue lah. Queue. So whenever you have some processors, in this case, it's being queued and then it's picked up one by one. So in this example, this is a poor lah. This is called a single-threaded UI lah. The UI is single-threaded, but there could be many things running, but this is single-threaded UI. Of course, nowadays when you click a button, let's say click a button and it says open file, you don't open file, you do asynchronous open file. Okay, so it runs a task separately from the UI to open the file. It can take 1 hour, who cares, but the UI is still responsive. Okay, so those are some of the things. And that's all for my explanation. The next one is talking about RTOS. Thank you very much. I can only accept a few minutes of question because I have another class at 12, undergraduate class. It is supposed to be 11 to 1, but I told them I can only have 1 hour class. So any questions, I can only accept 5 minutes. Other than that, thank you very much. No questions? Okay. I count 10 to 0, 9, 8, 7. This afternoon will be PM Munim's link. So by the way, PM Munim, the recording for my session yesterday is already in the same Google Drive, which I gave you the link. You can upload to your YouTube or share it with your students.
Okay,
Lee Sun Chong is asking when is test 2. Later, PM Munim will explain in the afternoon. Let the boss decide.
Sure, you should be here also to discuss.
Then we can discuss in the afternoon when is test 2. Yeah. Okay, so test 2 is bonus test. Tapi demand banyak-banyak is bonus. Right, PM Munim?
Yeah.
It's a bonus, right? Bonus means
whatever you can take. You be thankful whatever you give.
Yeah, but of course we are not going to put it on. Of course we're going to ask you lah when you're free and so on, right? But we'll schedule it with you. Don't worry. Okay, so I guess no questions. So if you have no questions on this completely theoretical based RTOS chapter, you can have a look at examples of RTOS and so on. I didn't manage to, or I didn't got the time to update these things. So probably some of the information may be outdated. For example, this is VxWorks 5.4. Current VxWorks is 7. I tried to find a similar diagram for the layers of that, but I couldn't find it yesterday. So I gave up. So I just leave it this one. I went to the VxWorks website also. I couldn't find this diagram. So until then, so it falls under the portion of examples, may not be updated. So you can have a look on this. Okay. So thank you very much from my side. I have to go and open the link again for my next class at 12. So thank you very much. I'll see you at 2 p.m. Please use PM Munim's link for the 2 p.m. session. Thank you very much. Assalamualaikum and goodbye.